Hello, everyone. Thank you for joining us, our second meetup of Global Feature Stores Meetup. This is the second one. We had the first edition in December, and we're very happy to bring Atindriyo from Uber and Monte from Splice Machine for this, our second edition. I'll pass it now to our Jim Dowling from Logical Clocks, who's one of the coordinators of the community, and he's going to talk a little bit about what we do, and we'll take it from there.
Yeah, hi. So thanks, Natalia. So as Natalia mentioned, we have the first talk will be about feature engineering at Uber with Michelangelo by Atindriyo. And then we're going to have Monte Zweben from Splice Machine talk about simplifying the feature store on their database. And we're going to conclude with a Q&A led by the other co-organizer of this meetup, Davor Bonacci from Cascada. So he'll be leading the questioning with Monte and Atindriyo. So who is, just to repeat, because we repeat this at the first global meetup for feature stores, we are featurestore.org, and it's an open community. You're all welcome to join. You're welcome to submit talks, and you're welcome to help organize events. So Davor Bonacci from Cascada and myself, Jim Dowling from Logical Clocks, we're the current co-organizers, but we want it to be an open community. We want more people to get involved. The community as a whole, we have a Medium page for publishing blogs. So if you have a blog that you want to write about feature stores, you can publish them there. There is a newsletter that gets published once a month. They're available on featurestore.org. So if you want to have your articles included there, or if you want to publish a blog, you can reach out to us. So one thing we thought about in the feature store meetups is we have a little news section because there's a lot of things happening in the feature store space. A couple of little news items that have happened in the last few weeks, even though it's been the holiday season. Today I saw that Molecular out of New York raised 17 million to build a feature store. I think they have something already, and it would be great if we had them here at some stage. And Igrazio have recently launched their integrated feature store in December 20. So new platforms are appearing, and I've heard rumors that there will be another big one coming out soon. So we'll expect lots of news items about feature stores. And then just a little pointer to the next meetups. We're going to have 2 meetups, hopefully in the next 5 or 6 weeks, from early February to early March. And a couple of the speakers that have confirmed already will be Simba Kader from Stream SQL, and then we have Pengu and Patrick from Airbnb. And if you're interested again in submitting a talk proposal, you can go to this link shown here. So I'm going to hand over at this stage to Atindriyo, and Atindriyo is leading this Michelangelo, which is the original feature store. I think it was the first feature store that that anybody published anything about, and that was way back in 2017, if I remember, August 2017. So it's really interesting to follow up on that project, which is the most mature feature store in the space, and see what exciting new things are happening there. Atindriyo, over to you. You can share your screen.
Sure. Yeah. Thanks, Jim. Let me share my screen real quick. All right. Can you guys see my screen?
Yes.
Yeah. Yes. Great. Thank
you. All right. So good morning or evening, everyone, depending on where in the world you are. I am Atindriyo Sanyal, and I'm a tech lead at Uber AI. And today I'll be talking about Michelangelo, and in particular, how we do feature engineering using Michelangelo's feature store palette. So there's a lot to cover, so I'll try to wrap it up in 20 minutes. So just to start with, like Michelangelo is an in-house machine learning platform that's used for the end-to-end process of machine learning, right from feature search and discovery to model training and serving and model monitoring. It enables data scientists and engineers at Uber to easily build and deploy machine learning models at scale. And this includes managing features for training, for serving, and the pipelines that compute them. It also provides a whole host of monitoring metrics, some being model-centric, like model drift, prediction accuracy, feature importance scores, AUCs, etc., and some being more feature-centric, like feature drift, online-offline parity, feature quality metrics, like how fresh your feature sets are, how many nulls are in your data, and so on and so forth. So before we kind of get into the weeds of feature engineering, I just wanted to sort of highlight a use case which I will sort of keep in mind while sort of explaining certain concepts. And that use case is essentially ETA for Uber Eats. And for a use case like this, some of the features which are used include how large your order is, how busy the restaurant is, and how busy the traffic is, and how historically quick the restaurant has been. So as you can see, there's already a mix of near real-time signals and historic signals as well. So how you build a feature store which encapsulates all these different kinds of data and provides like a consistent sort of API to access them is what sort of Palette is all about. So if you zoom into the feature engineering side of things, it kind of becomes obvious that it consumes a vast percentage of the ML workflow, and it involves computing from a wide variety of data sources, be it batch, streaming, RPCs, and serving them to models at scale. One of the chronic problems in ML that leads to models behaving badly in production is training serving skew. And a good feature engineering platform sort of provides on the online and offline tools to sort of track and surface this kind of skew. So for just to go back a bit, so for what we've realized is that for streaming features or near real-time features, traditional software engineering tools typically don't work. When you're dealing with tables and SQL, that sort of technology doesn't really work with streams, and streaming ML has sort of become pivotal in the recent past. And this is the whole world of extracting signals from Kafka streams and microservices. So that also is encapsulated within Michelangelo's feature store. So this is where Palette kind of comes in. And the goal is to sort of be a centralized store of curated and crowdsourced features. And by crowdsourced, I mean features which are contributed by different teams across the company. And it's kind of a one-stop shop to search for features. And features are typically around Uber's entities like restaurants, trips, drivers, riders, etc. And often we find teams building the same features again and again, which is not only is redundant work, but it's a massive waste of compute. And it's important that models sort of use the same data to avoid differences in the behaviors of different models that use the same features. So Palette kind of enables an ecosystem of tools around feature engineering that allows the data scientists to author production-ready features and serve and monitor them at scale. Palette also enables auto feature selection, which is an interesting area, and it involves selecting the right features for your models and ranking them using our in-house workflow infrastructure. And it sort of allows you to remove redundant features, and we sort of combine these tools with our, we have other tools around auto hyperparameter searches, and we're sort of enabling the data scientists, and we provide them to not only select the best features, but also kind of the best hyperparameters that lead to sort of the lowest mean square errors in your model. So if you look at the stages involved in the lifecycle of feature management, in the middle, you have the feature store, which is a data store of historic and real-time features, which is interfaced via an API. But the process of feature engineering kind of starts with feature preparation. Features are authored from raw data sources, which can be batch, streaming, or real-time microservices. Especially at Uber, it's a microservice infrastructure. There's like over 5,000 microservices which are running in production. Those also serve as a whole, like sort of a gold mine of signals which can be used in real time. And the process of providing the tools necessary for materializing these features from these data sources through a set of metadata. So on the right-hand side, you have APIs for feature search and discovery. And the feature store allows you to reuse features across models. And then auto feature selection techniques are there, which combine more ad hoc techniques like just removing redundant features which have similar distributions, to more advanced things like gathering insights from the models and based on that recommending the right features. This is where sort of the advantage of Palette sitting within Michelangelo takes place, is because we have a whole host of like model-centric insights as well, which we leverage onto our feature store. And then we also have feature transformations and imputations, which I'll talk more about. And these are essentially model specific. So Palette kind of provides common abstractions to organize features. And in the taxonomy, we have Uber entities, which are the business entities we make predictions on, things like rider, driver, eater. And entities have many features which are organized into feature groups, and which are set of features which are commonly sort of used together. And as a data scientist or an ML engineer, you bring your IDs and external features to the drawing board, and you use Palette's APIs and libraries to sort of join features from tables across the feature store through what we call Palette expressions. And these expressions are on top of the feature store, and they're agnostic to the kind of features, whether it's batch or streaming. So it makes feature retrieval very consistent and easy. So you can stitch together a powerful sort of production-ready feature set in 1 or 2 lines of code using Palette's libraries. And the library is consistent across training and serving, which is super important. And we kind of guarantee the latest, most accurate values of features when you call on a model to predict. It's backed by a dual data store system, primarily because the SLAs for training and serving environments, what we've seen are extremely different. And behind the scenes, we meet those SLAs without a user sort of worrying about the underlying infrastructure. So Palette has support for mainly 3 types of features. There's batch features, which are historical features, like some of the number of orders in 1 week, the average basket size of in the last 30 days. This is tying back to the use case I mentioned initially, to predicting the Uber Eats ETA. There's near real-time features which are generated, signals which are generated like a few minutes to a few seconds ago. And we have Flink as a service infrastructure, which allows you to do like minute level aggregations on these streams. And then you have just features which are extracted from RPCs, which are like endpoints. And they are typically like super real-time information, which requires like little to no latency, like location geohash, for example. So as I already said, like batch features, going really quickly through this, they're historical features, they're not time sensitive. And typically what we do is we have the way they're ingested into the feature store is through a feature spec, which encapsulates like Hive queries, which are run automatically via Spark jobs. And they materialize features which ends up in our offline feature store. And we have a dispersal mechanism to sort of take the latest values and the latest state of the features and make them available via a low latency store. And the APIs that serve the online and offline stores are consistent, which is super important for a data scientist, because number one, it's the API is consistent, so there's like less learning to do. And also it kind of guarantees you kind of get online offline parity out of the box as well. So near real-time features, again, they represent the latest state of the world. They're and generally they're aggregates across a few minutes. The life cycle of near real-time features is the opposite of batch features, where we essentially make the data available in the online feature store for serving, and we have auto ETL mechanism to make that available for training, and essentially make the same data available for training. An example is how busy the restaurant is. These kind of signals are leveraged from Kafka event streams at Uber. And then we use Flink to perform real-time aggregations. And then you have the real-time or RPC features, which are typically managed outside the Michelangelo ecosystem. So one of the interesting things is that we've seen is that certain features, the teams prefer to manage the lifecycle of the features on their own, primarily because they've already built out existing infrastructure to support the serving of those features, but you can still onboard them onto Michelangelo through a very spec-driven way. And you kind of get the other goodies of Michelangelo out of the box, like monitoring of the values of features and how they're influencing the models. So Palette joins data across different entities and different feature groups, and the API exposes common abstractions like palette expressions to represent a feature. And behind the scenes, we join data across different feature sets and provide you with like a consistent API in an online serving as well as an offline or a training environment. And as you can see here as an example, what you bring to the table are what we call basis features. And they're typically IDs, like the order ID or the restaurant ID. And they can be features which are managed outside the Michelangelo ecosystem. You bring that to the table, and through what we call palette expressions, we do an ID and timestamp based join. And you can essentially create like a feature data frame for training. And behind the scenes, we do the nuances of the joins and the Spark optimizations based on the size of your data sets. So those things are kind of abstracted away. And what we've seen is that like data scientists want speed. So it's important to sort of abstract out the infrastructure, but yet give them the flexibility to sort of provide certain aspects of the compute, like the number of Spark executors and other system level parameters, if they choose to. But then we have, of course, we have default configurations, and behind the scenes, we have ways to figure out whether how to make the joins very efficient, because these joins are across like tables at Uber have like 3-4 billion records. And we do a lot of like these Spark-based optimizations to ensure that the jobs run fast, but also through these expressions, we allow them to do things like time shifting and date shifting to avoid things like future leaks, and those are sort of chronic ML problems. So feature transformation, it includes fetching features and transforming features from the feature store, but also doing operations and imputations on them. So as Palette is kind of engineered to be in accordance with Michelangelo's transformer abstraction, which is further an extension of Spark transformers, it allows us to sort of construct feature pipelines that enable you to do these transformations and imputations in a very easy way. And we've built out, like we have built an infrastructure to run the transformers in both an online offline training and an online serving environment. And feature impute is achieved via what we call DSLs. And DSLs in our world are these idempotent operations you want to do on features to generate a more relevant feature for your model. A simple example is you take the latitude and longitude and you convert that into a geohash. And a lot of these tools, as you'll see, they sort of meet the data scientist where they work. So when we construct an ML pipeline, we provide all these tools and libraries to be able to build models and do feature engineering as part of that. And that's important because you don't want feature engineering to be too different from the model development process. Otherwise, it kind of becomes a bit too intrusive. The idea is to sort of have a seamless way and a flexible way to do feature engineering while you're sort of doing the model development. So as I mentioned before, Michelangelo conforms to the standard Spark transformer and estimator interface and extends it to work seamlessly both online and offline. And the offline version is the transform method, which typically is basically data frame in, data frame out. And the online version we've extended support for is a simple sort of map in, map out interface. And it adheres to like the ML readable, writable contract, which is a Spark serialization construct. And this enables us to save and load these transformer chains very easily. And typically, you would write a UDF, which is a user-defined function that would be leveraged in both training and serving environments. And that's one way to ensure parity in the feature transformation. But we also have like a homegrown unit testing framework that allows you to assert the online-offline parity of any given transformer. So we've seen that all these tools, especially around like unit testing and things like that, sort of nip the problem in the bud by adding more tests around online-offline parity as you're sort of developing a custom transformer. So palette as a transformer, it basically means that while training, you return back a data frame of features. And while serving, you serve a feature vector of the latest values of the same features. And the model execution engine runs both the online and offline code behind the scenes, depending on whether you're training or serving your model. And now expressing palette as a transformer gives it a lot more power because number one, your online and offline transformations are now abstracted out. And number two, you can stitch together a more complex ML pipeline with multiple feature engineering transformers, and which enables you to do things like transitive feature lookups. And with our DSL engine, you can do more sort of downstream calculations on your features. So as an example, say you want to calculate how busy a particular region is. You extract the lat-long information from the feature store. You use DSLs to compute the region ID from the lat-long. And from the region ID, you can again query the feature store to get information on how busy a particular restaurant is. So let me talk a little bit about DSLs. So DSLs essentially are designed to do like downstream imputations on features, which are retrieved from the feature store. As you can see, when you declare a DSL is designed as an estimator, because you fit a data frame into the estimator and you get a DSL transformer. Behind the scenes, this is just standard Spark ML lib lingo. And the example here, you can see two DSL estimators. The first one, what it does is it takes in two palette expressions, which represent the latitude and longitude, and computes the region ID. So you can see like the region ID is a function. There's a little bit of a typo here. The quotes should be in the expressions, not in the function itself. But the high level idea is that sort of these are these idempotent lambdas which can do imputations on your features. And these lambdas are, we've optimized them to sort of be serialized as bytecode. So whenever you load these lambdas into your JVM, whether it's for training or serving, they're sort of loaded, the class loader kind of loads the bytecode itself, and we avoid those additional latencies that are associated with parsing and compilation when you're serving features. So here, the top one computes the region ID from the latitude and longitude, and you have a second DSL estimator, which computes how busy the restaurant is from the above information, and you can do more. You can apply more lambdas to them, like stuff like nfill and nval, which essentially means if the value of a particular feature is null, you want to replace them with the average, or you can replace them with a static value, etc. So it just makes just construction of feature sets which are compatible with models a lot easier. So I already covered this a little bit. So the DSLs themselves are kind of optimized, and we save them. We sort of do code gen behind the scenes, and we save the bytecode, which is then loaded onto the online and the offline class loader, whether you're training or serving your models. And that allows us to not sort of make the transformer execution slow. And so just to sort of step back and uh, create a sort of transformer pipeline from the stuff I've already spoken about. Uh, Here you see this is an ML pipeline which has 4 stages. You take the palette transformer and you compute these 3 features, the end meal and prep time and the latitude and longitude. You inject the latitude and longitude to extract a region ID. You again stitch a new palette transformer to compute how busy the restaurant is from the region ID lookup. And then finally, you can do more imputations like nfill and nval just to make sure that the final feature set is salient. So all these things that I've talked about, whether you're creating features from Hive or Flink and a lot of the transformer libraries, they're all basically dev tools for authoring an ML pipeline. Palette kind of meets the data scientists where they work. So all these are exposed as libraries within sort of the Michelangelo Spark Transformer framework. And behind the scenes, we sort of save a transformer chain as a model using the ML readable, writable constructs. And that allows us to basically load the same transformer chain in an online environment and execute them without writing any additional code. The last piece I want to talk about is feature quality monitoring. And this is, I'm sure this is preaching to the crowd, but the models are only as good as the data that you feed it, and feature pipeline breakages are extremely common, and poor insights into the data at training and serving time leads to the models sort of behaving badly in production. And there's the common issues include, there's missing data, there's null features, there's sudden drifts across the data, there's inconsistencies when you have data failover, etc. So the idea of quality monitoring is to, number one, measure the data quality of the data that's going into your models. You want to enforce data hygiene through things like SLAs and really tying the SLAs of feature sets to the models, because not all models are not all models are tier 1 models. So the idea is to ensure that tier 1 models use tier 1 data sets and so on and so forth. And then finally, we want to have accountability through ownership information that's provided as part of the metadata, so that number one, you can reach out to owners of feature sets if the health of a feature feature group sort of goes down. But then also we do like we calibrate feature quality scores, which are essentially aggregates of different kinds of feature tests that we run on all our feature sets. And then we sort of expose that score as an aggregate. So it kind of gives you a good bird's eye view of the health of your sort of feature warehouse. And this whole system is kind of self-servicing in the sense that there's little to no intervention on part of an engineer who wants to author features. These tests are automatically registered. We have a standardized set of tests which compute missing data, freshness, duplicates, and consistency across data centers, things like that. But we also have the ability to add custom tests for certain feature sets if needed. And these the scores of these tests are sort of surfaced to the user, both at training time as well as serving time. And we sort of hold accountability around the quality of these features. So again, it sort of ties into the existing feature store infrastructure, where we have a sort of a system which registers tests. Tests are of 2 types. One are, of course, for the offline feature store, which are more around just the quality of the offline feature tables. But simultaneously, we have tests around our online store, which measures things like online drift, and we have real-time alerting around that. So the key takeaways are essentially, spoke about the core feature store, how features are prepared, how features are joined together to build data frames and feature vectors, how feature engineering is done as part of transformers, DSL estimators, and how you construct ML pipelines of using these transformers. All these are dev tools for feature engineering, and feature quality monitoring is a first-class citizen. So yeah, that's about it. And of course, just a little note, we are definitely hiring and trying to grow. So if you're interested in Uber AI and want to do like cool ML things, feel free to drop me an email.
Great. Thank you very much, Atindriyo. Let's take a quick question. It's in the Q&A, but I can read it out if you can't see the Q&A. How do you handle cases where some feature transformations have to be done after fetching the features from Palette? Or do you expect all feature transformations to be part of the feature engineering pipeline?
No, that's a good question. So the entire feature engineering pipeline is not fully Palette. So parts of it are Palette. So you can do, it's very flexible in the sense that you can do computations using DSLs, etc., which you can apply on top of Palette expressions, and Palette would sort of handle those things. But then not every computation is super simple. So that's where these DSL estimators come in, where you can, which is not part of, it's part of the Michelangelo ecosystem, but it's not a native part of Palette. And the idea there is that, yeah, you have some custom logic where you want to do more than just, these idempotent simple operations on the data. So you can create a custom sort of DSL transformer where you can write your logic, and it automatically extends the Michelangelo transformer framework. So behind the scenes, we would just run them in the order that you specify in your pipeline. Yeah, I mean, we've seen cases where, yes, particularly around, say you extract features from RPCs and they're massively nested JSON objects. And there's a lot of complex sort of parsing that you'd have to do of the output in order to extract the right features. So in those cases, we allow them to sort of write custom transformers as well. And that sort of is part of the Michelangelo code base.
Okay, thanks, Atindriyo. Thanks, Faisal and Anis, for answering the question. So I think we'll move on to, if there was another question, but we'll move on to the Q&A at the end. We can move that if we need. So now we have Monte Zweben from Splice Machine. He's going to talk about simplifying the feature store. And I think this may be the first feature store where we have not a dual database, if that's correct, Monte. I don't want to steal your thunder, but just to lift the kind of spirits of the listeners and think, yeah, well, this could be something very interesting to see.
Yeah, thank you, Jim. I appreciate it. Can you see my screen?
No, we can't. So I think you need to share screen.
Try it once more.
Yeah, now.
Now?
Great.
Yeah.
Okay, excellent. Yes, you stole my thunder. That is the punchline. But a little story behind that is the founding of Splice Machine and what went into it. It was essentially this idea that we experienced both in a former company that I had started called Blue Martini, when we didn't have a big data architecture. We just had Oracle databases, but we were deploying machine learning models in operation. And much more recently at Rocket Fuel, where we were using machine learning to essentially put the right message in front of the right person at the right time in a classic ad tech and marketing tech application. We had armies of engineers utilizing online and offline stores to do feature engineering. And we had an incredibly complicated, multi-petabyte, very large set of data that was in the old days using MapReduce combined with HBase in order to do online, offline. And then Spark came along, actually Hive came first, and we were able to use Hive and HBase, and then Spark and HBase, but it was a mess. And so the idea behind Splice Machine was to build a data structure and a database underneath the modeling environment that could simplify this entire infrastructure. We didn't have the word feature store then, but the whole idea of what engine we created was really motivated by the complexity of the underlying data structure, and really excited about the community we're building in essentially focusing on this particular problem. I'm so excited about it. I'm writing a book on it, and I hope that everyone here in the community will take my calls and talk to me about things so that we could incorporate some ideas in the book. But this is coming out next year. And just to get to the heart of the matter, as we just heard, data comes from lots of different sources. In most machine learning circumstances, feature engineering takes the large majority of the time for everyone to work on. Some of these features may be extremely real time, like the RPCs we were talking about a moment ago, and other events that are coming in. And you might actually have machine learning models be the features to other models. And we go through these pipelines, and feature stores are essentially performing both the real-time serving and the construction of feature sets, as well as being searchable and discoverable. And we also talked a little bit about a moment ago about governance and being able to do transparency. So as Jim said, the punchline for us that we were trying to attack is, how can we simplify this? And, just as we heard about, trying to keep parity between online and offline stores, is there a way that there can be one store? Can we build feature stores where there is only one data layer, one online store and offline store? And we think the answer is yes. And what we've done is build an HTAP database, or what Gartner calls HTAP, hybrid transactional and analytical, or just OLAP and OLTP, ACID compliant database. That's what's at the heart of our feature store, that I think significantly simplifies feature stores in general, and enables the data scientists and the data engineers to operate at a SQL level in a very efficient way, and even enable feature stores for those that may not be Spark specialists. If you are a Spark specialist, that's great. You'll see how we do things. If you're not, it's an environment where you can actually just use SQL. And the benefits of having a single store, a simple feature store, are manifold. First, it is easier to provision and operate a single store than multiple stores. There's less infrastructure cost to power them. It's easier to back up and replicate in a real production environment. And you can really use some native database capabilities to be more event-driven, like triggers. And we believe that this parity can cause latency in some feature stores, and perhaps by having one SQL-based feature store engine, you don't have that synchronization problem. So what's at the heart, and how do we enable this? It's a dual SQL platform. It literally is a SQL database that is ACID compliant. It has all of the capabilities you expect in a comprehensive SQL database. It even can support running other old SQL applications. We have some customers, for example, that are using the underlying data engine here and not having to change their code from, say, DB2 application. So it's a robust SQL engine. And the way it works to power the feature store is that it introspects the queries and determines from statistics whether a query is essentially going to have a large result set or a small result set, or operate on a large set of data or on a small set of data, and then uses the optimizer to compile into bytecode the instructions to execute the query on the appropriate engine under the covers. So if you're doing a single record lookup or a small range scan, like here looking up a particular order line item, our optimizer would be able to know that this is indeed a single record lookup. There are primary keys or indexes that would be able to identify this very quickly, and the data is actually, and this is actually executed, this query is executed on Apache HBase underneath the covers. And we orchestrate all this automatically, and you don't have to operate HBase as if it were a single component. It's all Kubernetes architected. And then if there's a feature pipeline that's doing a very complicated set of joins, aggregations, and groupings, we actually execute that in Spark underneath the cover. So it's a Spark-based database that's memorializing data in an ACID-compliant way in HBase and being able to do the OLTP executions there. And just like almost every other feature store, we use primary keys to help abstract away the complexity of building feature pipelines. For example, just like almost every feature store out there, business entities have primary keys. We use what some people call feature groups. We call them feature sets of features that are grouped together and change at the same cadence. For example, a customer ID might be able to be used to identify individual customer spending or individual customer demographics and individual features that are all changing at the same pace there. And we also abstract away the point in time consistency problem. This is such a big problem, and there's so much code that one has to write if you don't do it automatically. We just heard about it a moment ago, but just as a recap very quickly, in a problem where one is making predictions in the middle of a customer interaction, and you have a number of features, perhaps like number of searches and items in a cart and how many products were viewed. These features are all changing over time, and one has to align each of these features for training examples and be able to do that historically. And this is tough to do if you have to do it manually. And so this one slide, I think, is the best slide that gives an engineering understanding or a technical understanding of what's happening under the, behind the scenes in the Splice Machine feature store. It's automatically maintaining a sort of online offline view in the same engine, and it's using the fundamental components of a database, an ACID compliant SQL database, to do so. And we do believe that SQL is a great basis for a feature store, especially for those companies and those entities in the world that may not be familiar with big data architecture. They may not be Spark houses. They may not be really growing up through the MapReduce, Hive, Spark, Flink sort of world, and just want to use SQL. And so what happens here? In the Splice Machine feature store, arbitrary SQL can be written to help, and we'll talk about how we abstract away some of that SQL in a moment to make it easy. But all of the pipelines that are taking place, that are doing roll-ups of data, like we just heard about before, historical roll-ups, that may be doing recency, frequency, and monetary value aggregations or other types of aggregations, update a feature set table. And a feature set table is essentially the current values of the features in that feature set. And it is got a primary key that will identify, obviously, one customer's features from another customer's features in a customer-facing application, if that's the primary key for the feature set, just to use an example. And it's indexed also by time here, that or at least shows, has a timestamp of when the last update is. And the key here that's exciting about the simplification of the engine is that the online offline world is automatically synchronized in real time. And it's done through a database trigger. So if some arbitrary SQL in a feature engineering pipeline changes the features in a feature set, the system will be able to automatically take the old values of the features and store them in a time series representation with an interval of time that will essentially power the point in time consistency later on when we're building training sets. So summarizing that again, arbitrary SQL is being used in feature engineering pipelines. That arbitrary SQL is essentially ending up changing a feature set table. These are all declaratively represented in our API, and I'll show that in a minute. This is using Splice Machine's row-based storage for the most part. We also have columnar storage too, but that's a separate conversation for another time. When you change features, then the feature history is populated with the older value of the features. And that is what's used to form training data. So we think this is a really great way of simplifying the entire architecture of a feature store by utilizing these database capabilities. So just as maybe a more broader view now, abstracting back out from the implementation layer, just as the API layer, how do we go about building these training sets? And I'll just give kind of a flyby of the big training APIs and concepts that we use. Simple training sets are really easy to do. You just simply say get training set and specify a set of features, and you can give a time interval over which you want those features to be collected. And this is the simplest case, but often creating training sets are more complicated. And we have a training set spec as well that abstracts away this idea of building a training set so that you can reuse a SQL view almost that gives a time series view of all of the features. And the way it's specified is similar to the way other feature stores do this. I won't go into too much details, but a training view lets you specify exactly what the primary key values or columns would be to identify the entity that you're working with. It identifies the join keys that will join together both the data that's in the feature set tables and any arbitrary data that might be outside the feature store, like we heard earlier in the Uber talk about needing to do that. And that is often the case when you're trying to combine together the features with labels. So this lets you specify the SQL necessary to join a bunch of features and arbitrary SQL that'll allow you to tie the label together with the features. And you specify what the timestamp column is to do point in time consistency and what the label column is. And this creates a spec of SQL. It doesn't actually create training examples yet. It's kind of a spec for that. And then you can use that to essentially make a training set, to instantiate a training set. And here you take a training view, a time interval with which you'd like to have a set of training examples or training cases. And then one nice element is that it allows you to specify the individual features that are in those feature sets that you'd like to use. And this calculation here, get training set from view, does all of the point in time consistency that we talked about earlier, again, used in one engine, the underlying data store there. So our feature store fits into a larger architecture, and I just want to maybe abstract away now even one step further and talk a little bit about some of the benefits of how this feature store that's simplified by having one data engine, how it fits in with some of the other componentry in a machine learning architecture similar to Michelangelo. What we've done is try to take some of the best practices of various machine learning systems like Michelangelo or the Zipline feature store and the other elements of the Airbnb system and some of the other larger scale deployed operational systems, and just make a turnkey package that people would be able to utilize. And so I'd like to talk about how our feature store fits in with modeling, experimentation, and deployment elements very quickly here, just to give a little taste. The modeling environment is a Jupyter environment. It's using similar tools to what everyone would typically be familiar with. And it also incorporates some already built-in machine learning frameworks, and it's extensible so that you can add any new ones. But the key point about the Jupyter environment within the Splice Machine architecture is something called a native Spark data source. And this is kind of similar mechanism to perhaps some of the DSLs that we were just hearing about. But what it does is, what we often hear is, oh, SQL databases aren't really great for doing pipelines and for working in machine learning. But we have tried to bridge that gap and make that actually not true by providing a pattern to SQL operations that can utilize our ACID compliant database, but in a kind of Spark-like manner. And so what we do is essentially expose a native Spark data source that takes the underlying Spark executors in a complicated OLAP query, and we expose those instructions as data frames back to the user. This is to be contrasted with a traditional database. You go and essentially ask for a query, the database serializes the result set back, and you deserialize it, put it into a data frame. Instead, what happens is you issue SQL, and what comes back is a set of instructions. So you get to take advantage of lazy evaluation. And this is kind of like making a persistent CRUD operations for Spark, and that'll be useful in a minute when I talk about how it all comes together. We've also incorporated ML flow so that you can denote what experiments you're working on and refer to machine learning models. And finally, getting to deployment, almost everyone in the world is using traditional endpoint deployment models where you're wrapping an API around the model, perhaps building a service around it, maybe even containerizing it, and potentially pushing it out to a scale out container manager like SageMaker or Azure ML. And we do all those things too. And we have a Kubernetes architecture that does that, but we have another kind of deployment that works very closely with the feature store. And what we call this database deployment. And it's a very simple idea. Again, simplifying the feature store with one data layer also simplifies deployment of those features connected to models. How? With one line of code or a click in a user interface that's emerging soon, one can take a model out of ML flow, any one of the run IDs, and say deploy. And what that will do is automatically introspect that model, see what features from the feature store are used, and create a table that is essentially called a prediction table that has a column for each of the features that are in that model. And then a trigger is automatically created that makes this pipeline take place in real time when you add new examples to the prediction table, like adding records here with features by a particular person at a particular time or a particular application at a particular time. The underlying mechanism actually calls a trigger. The trigger runs the model, and the model inserts the predictions directly in the table. This is pretty cool because no endpoint programming is necessary. It's really fast in the database because it is essentially executing this with OLTP latencies. This really gives you inline prediction at sub-millisecond speed. We've scaled this pretty significantly, and we'll report some benchmarks soon. But what that does is it memorializes all your data and your predictions in tables. And so we've also incorporated instrumentation for reporting on that those tables, so we can look at model drift and feature drift inside of dashboards that are exposed in Grafana, and essentially it makes this time series modeling of what the models are doing, what the features are doing, really easy. And this presents a different layer of transparency than perhaps one gets when just using Spark or some of the other engines that are available out there. Database deployment allows, as we just showed, those tables that says, okay, for any prediction, what model made that prediction? What was the run ID? And we can go back and see from that run ID in ML flow, what were the features, hyperparameters, and an algorithm used in that particular prediction. And then, of course, the feature store gives us the transparency and the feature history tables that are, again, exposed potentially as very clean dashboards, or perhaps looking at nice plots inside of notebooks. What were the features? How were they computed? And then lastly, and perhaps most exciting about the underlying simplification of the data store, we even have time travel, where you can jump back in time to when the database, the snapshot of the database when the model was trained, and not just look at what the feature history is, but look at the raw values of all of the raw data back when those training sets were created and when that model was trained. So kind of a nice combination of a feature store with database deployment ends up with some lineage. So our aspiration in closing here of what we're trying to achieve technically with our approach to feature stores is to take a feature store that we've created, combine it with ML flow and database deployment, and provide just a better, speedier, more agile environment. And our goal is to try to make organizations really, really fast at their experimentation and their deployment, and hopefully have a lot fewer engineers because they don't have to have an online offline type of environment, and they have all of these components put together. So this was a little bit of a high level presentation, and I really appreciate the opportunity to present, and thanks to Jim for letting us as part of the feature store community. We really want to be an active member of the community. We're co-sponsoring the TWIMLCon event that's taking place next week and the week after. And if anyone wants to get a kind of hands-on view of our API and the entire platform, we've got a half-day workshop taking place on the 28th that you can sign up for. And we'd love to have members of the feature store community come on board. And just to leave some final words, it is an open source feature store. It's modular. As I mentioned, it's integrated with ML flow and database deployment to provide a new level of transparency. And the whole point of the talk today was just to make the case that it's a more simple architecture that has one data layer that is simultaneously an online and offline store and uses database triggers to maintain that uniform representation. We're hiring also, looking for community members too. We're open source, so if anyone wants to work on it, but maybe not work for us, we welcome that and look for members to join our ecosystem and community. And for demos and trials of the platform, you can go to splicemachine.com. So that's my presentation, and thank you very much for spending time with us today.
Thank you, Monte. All right, so we'll switch to Q&A session. Q&A can be about the presentation, about the meetup itself, about the group, about future talks, literally anything goes. Right now, there are no questions in the Q&A session, but please raise your hand or post a question, and then we'll get there. And I'll start with a question before we get questions from the audience. For both of you, I guess, what's the future roadmap, and what do you plan to do in the next few months or next few quarters? What is in your mind in the future?
Well, that's to me, right? Okay, that's great. So our roadmap is it's robust. We have more that we want to do than we have the time and capacity to do so. That's why we welcome other members. But first and foremost, we want to deliver on an extremely performant and scalable feature store that is really flexible for engineering organizations, data science organizations to be able to build in production machine learning, and even to do so utilizing SQL. The first deployment of the feature store is a robust API. The second delivery is a full user interface on top of this to make it even easier. So those are the most important two things that we're delivering on. And then shortly thereafter, robust capabilities for backfill is really important. And I really loved what we heard earlier about the automatic testing of features. Now, that wasn't originally in our roadmap, but that was, Atindriyo was really insightful about what they did with Palette and Michelangelo, and I think we're going to add that to our roadmap. So those are the few things that we're doing as well.
Thank
Any
you.
other questions?
Oh, are you asking?
Michelangelo, what are you thinking in the coming months?
Sure. I can probably just talk generally. I'm probably not allowed to speak about Michelangelo specific things, but I think high level, what Monty talked about pretty much nails it. There's infrastructural improvements for performance and really simplifying the scale problem of feature engineering. That's definitely a big thing that's gonna sort of be at play in the next few years. That's one thing. But I guess just to add to what Monty already said, yes, data quality is super important. In the end, you're trying to solve like the high level problem of making models more robust and more accurate. So data quality is huge, but also I also feel just in general, the librarization of feature engineering is also very big.
Yeah.
And essentially, eventually, I sort of see feature engineering and just model engineering sort of converging into certain common abstractions. Like Spark has already provided like the transformer interface where it really becomes easy to construct these ML pipelines. So there will be a lot of progress on having feature engineering as part of these common abstractions, just to make model development easier and easier.
Yeah, I concur with that. That's great.
Perfect. I don't think we received any more questions, or Natalia, I think, answered the question in writing. So I think we are kind of on time. So I think we should end here. Thank you to both speakers, obviously, for sharing their wisdom with the community. In the coming weeks, we'll have more instances of this meetup. Airbnb talk is coming in the coming weeks. Stream SQL talk is coming in a few weeks. Jim and I will talk again. So we'll figure out the schedule, and it will come up. Please subscribe to the newsletter. Please subscribe to the meetup group. You'll get the updates as soon as we figure out the next steps. Thank you for attending today, and I hope to see you soon.
Thanks, everyone.
Thank you.
Thanks, Monte. Thanks, Atindriyo. Bye.